In this video, we're going to talk about the wireline communications channel. What that means is that the transmitter and receiver are connected by literally a wire. It also could turn out it means it could be optic fiber. It just depends on which situation. These kind of channels have very different characteristics than the wireless channels discussed in the previous video. And let's see how that works. The wireline channel have a dedicated piece of wire connecting them. That's the idea. Could be more than one transmitter and one receiver on a given piece of wire. That turns out to be the way Ethernet works. We're not going to talk much about that, but basically that is also a wireline channel. In designing a wireline channel, Maxwell's equations come into the act again because you have to minimize what's called crosstalk. So let me take a simple example, which is known as the two-wire pair. You need two wires because let's assume a sending station is a voltage source, and you can't apply a voltage except if you have two places to apply that voltage. So you need that's why you have a two-wire pair. And let's assume the receiving system looks like a simple load resistor, for example. Well, suppose there is another two-wire pair sitting over here. Well, it turns out both of these pairs look like antennas. What is sent by one will be picked up by the other. That's called crosstalk. And in general, this is a very bad situation. It's like you picked up your telephone and all the telephone calls currently active in your neighborhood, you could hear them all. Particularly, that's not probably what you want. Well, it turns out a simple change in that two-wire system can mitigate the crosstalk, and that is by twisting the pairs together. So you take the two wires and literally twist them. It's called a twisted pair, and greatly reduces the crosstalk. It turns out if you solve Maxwell's equations for this much more complicated geometry, you can see that the crosstalk is greatly minimized. An even better way of minimizing crosstalk is to use what's known as a coaxial cable. And here I show a photograph of a piece of coaxial cable. You might recognize this as kind of TV cable that you use to connect to especially cable TV, but it's also used for the electronics in cabling televisions together. And here I show a cross-section of what it looks like, and here's a real live cross-section of my piece of coaxial cable. So the black part here is insulation to keep other wires from touching it. And inside you see this copper. That bright orange just gives away copper. So that's one of the conductors. In between the central conductor, here's the other one. In between those two is what's here white. That's a dielectric. In this case that I'm showing you, it's Teflon. It's a dielectric, especially designed for the piece of coax. And so a voltage is applied between the outer conductor and the inner conductor. And that's how the signals is sent. And it turns out if you solve Maxwell's equations for this geometry, you'll see that it basically does not radiate at all. It leads to a very good approximation. So multiple coaxial cables can carry separate communication signals without interfering with each other. And that's good for wireline channels. Now, we need to explore the properties of the wireline channel. It's very interesting. And again, going back to Maxwell's equations, you can show that this circuit model I show here just well describes Maxwell's equations for the coaxial cable and for the twisted pair for that matter. So here's the idea. This is the model for a very small section of coaxial cable of length delta x. Each section of coaxial cable is described by a resistor in series with an inductor, and then there's a parallel chain of another resistor and a capacitor. Now you notice the tildes over the R, L, G, and C. Our tilde is resistance per unit length. So that's why the resistance here is R tilde times delta X. Same for the inductor. This resistor that's in parallel, it turns out its conductance is going to be a lot more useful in our final formulas, so I show it as a conductance per unit length. This conductance per unit length here is different than this resistance. They're not the same at all. So, what we need to do is figure out how the complex amplitude of the current at position X is related to the complex amplitude of the voltage at position X. So I'm assuming that the voltage, let's say, at position X is equal to the real part of some complex amplitude times a complex exponential. So this should be voltage as a function of x and t. So right away assuming a sinusoidal source, and everything we know about impedances and everything will help us figure out the relationship between the voltage and the current. So what I'm going to do first is go back to fundamentals. Remember Kirchhoff's current law, KCL? Well, we need it right now. So I want to write KCL at that node. So the current coming into that node is I of x minus delta x. The current going south is given by the sum of those two currents, and that's given by the voltage across them divided times their conductances and admittances with the delta x. And that's equal to the current that's leaving, and that's the I of x. So that's KCL at that node. We're going to write KVL around one loop, and we'll pick that loop. So this voltage is equal to this voltage, which is given by this, plus the voltage across this parallel combination, which is just the voltage out there. So I think you see where this is headed. I'm now going to rearrange the equation, let delta x go to 0, and arrive at a set of differential equations, one for the KCL equation, one for the KVL equation. Well, I want to get one relationship here, so what I'm going to do is take a derivative of this equation, which gives me a second derivative here for the left side, and on this side that gives me a derivative with respect to x. And now I can substitute in that equation down below and arrive at a simple equation for the complex amplitude of the voltage at a given location x. And it turns out to be a very simple differential equation, as we're going to see in a second, where the second derivative of the voltage is related to the voltage times a frequency-dependent constant. It does not depend on x, that's why it's considered a constant, but it is frequency dependent. We'll see how that works out in just a second. So, turns out the solution of this equation says that voltage propagates, just like in, as you might expect, because it's governed by Maxwell's equations. So, what's going on here is I'm going to call this gamma squared. And if you substitute this assumed equation into this equation, I'm sure you can see that when I take a second derivative of the voltage, that brings down gamma twice, giving me a gamma squared, and I get two solutions. The reason for the V plus and V minus we'll get to in a second, but you can have either a plus or a minus in the signs in those exponents. And that solves this equation. So, that's the differential equation. We see that the solution looks like this. And gamma is this rather complicated function. It turns out simplifying this is really not worth it. It doesn't really simplify very well at all. You can certainly multiply these two complex numbers together, but taking the square root means converting the polar form and trying to simplify it, and it just doesn't simplify it. I suggest you try it for fun if you have a very strange sense of fun. It's not very nice at all. But suffice it to say, we know it's a complex number, so it has a real part and it has an imaginary part, and those are the critical things we're going to need. Now, we're going to assume that we always pick, and you can prove that this is true, that the a variable is positive. So, if you go back up to our formulas and stick in the solution here for what gamma is, if you had a positive, this says for x greater than 0 that this will decay, right, e to the minus ax. If you assume that for x positive you had the other term here, that would mean it would blow up. It'd get infinitely big. That's a non-physical answer, so we throw it away. It mathematically fits, but it doesn't fit the physics of the situation. Power has to be conserved, of course. So that's why the plus and minus. This is the signal you get on the positive x-axis from where a source might be, let's say, that's applying a voltage. And for the negative side, you get that for an equation. All right, so to put it all together, the voltage at a given point on the coaxial cable and in time, notice this is a lowercase v, so I'm using my real part. This is the critical part. I'm about to show you that when you have a solution that depends on 2 pi ft minus bx, that corresponds to a propagating signal. And that's real important. So let's proceed to show you that this formula does mean that voltage propagates. What I'm going to look at is this exponent up here, and I'm going to think about it, evaluate it at the time t2 and let's say location x2. Well, I'm going to add and subtract t1 here, and what you find is that this expression equals the same quantity at a different time and a different location x1. The separation between x1 and x2 is given by this quantity. So let's plot what's happening here. Let's say that's x and that's t. We're at x1 and here's t1, of course. If we go out to x2, we're at time t2. And the signal here at x1, t1 is the same as the signal at a different location and a different time. That means the signal propagates. It's moving from the x1, t1 location to the x2, t2 location. So anytime you see a signal that depends only on time and space like this, it means it's a propagating signal. So let's examine this more carefully. How fast is it propagating? So if you look at the units inside here, you see that's distance and that's time. So that means this quantity has to have units of speed, of velocity. So the speed of propagation, just by unit analysis, is related to b. And once we know that, we now can calculate the wavelength. And the wavelength is given from this classic formula which applies to all propagating waves, that the wavelength times the frequency is just the speed of propagation, so we find that the wavelength is 2 pi over b. Well, what's b? Now, if you recall, b is this equals this imaginary part of the square root of gamma squared. It's equal to the imaginary part of gamma. And it's a complicated expression. It turns out if you analytically try to find that square root, it's really quite difficult. And what I want to do is point out that it really simplifies, though, if we consider a special case, and that is when frequency gets big. When frequency is big, you can drop G tilde with respect to that term. You can drop R tilde with respect to that term. And so what you wind up with is J 2 pi F C tilde times J 2 pi F L tilde. And that equals minus 4 pi squared F squared L tilde C tilde. And we now have to take the square root. Well, the square root of this, because of the minus sign, is pure imaginary. And that's J 2 pi F square root L tilde C tilde. So the imaginary part is just J is 2 pi F square root of L tilde C tilde, and the 2 pi F's cancel, and lo and behold, we find that the speed of propagation is depend only on the characteristics of the cable, and it's equal to that quantity. Depends only on the inductance per unit length and the capacitance per unit length of the cable. Most well-designed coaxial cables, the speed of propagation is about a third to a half of the speed of light in free space, so it's certainly not free space, but it's not far away from it, just a small factor difference. Well, that's the propagating part. How about the attenuating part? What is A? Well, we know that A is given by the real part of gamma, and it's a little bit trickier to show that the real part is not zero. We've already shown that as frequency gets big, it looks like the imaginary part dominates, and that's true because it turns out that imaginary part is proportional to frequency. But there is a small real part which does not depend on frequency. It's a constant as frequency gets big. And it's easily seen once you do the analysis, which is in the notes, that A becomes this quantity depends on the resistance per unit length and the conductance per unit length of the cable. And Z naught is a quantity we're going to talk about in a later slide, later part of this lecture, and it's the square root of L tilde over C tilde. And this quantity shows, once you figure out what it is for standard pieces of coaxial cable, this can be large. This can be 100 dB per kilometer if you're not too careful at high frequencies. Turns out this attenuation factor is smaller at low frequencies, but if you operate the cable at low frequencies, the speed of propagation will now depend on frequency, and you'll get different delays for different frequencies, and we've already seen that won't be a very good situation. So wireline channels have the problem that the signal can attenuate very rapidly. Now it turns out these equations also apply to optical fiber, and you'll find the attenuation factor is much smaller, and you can get 1 dB per kilometer or even less for very well designed optic cable, but for coaxial cable it's a different story. Now, I just want to point out that of course the current propagates also. So we've been talking about the voltage here, and as you remember, one of our differential equations was that for relationship between voltage and current, so I can just take the derivative of my expression and I've solved for the current. And what you get for an answer, after all is said and done, plugging in for gamma, is that the current is given by a very similar expression. The important parts are in the exponents here. So we get the same kind of thing in that the plus side goes for positive x, and the negative one goes for negative x. Similar kind of things happen. The current also does not diminish, so this goes to 1 in the high frequency limit, and this corresponds to a propagation. So both current and voltage propagate, as you might expect. But what's really interesting is this little result, which we're going to talk about a little bit later. Looks like the complex amplitude of the current and voltage looks like the impedance, which is that ratio, depends on frequency. But we have a little surprise for you. So let's summarize. The voltage on a piece of coax at any given point in space, when you apply a sinusoidal source, is given by this expression, and if things are designed right, this goes to 1. So, and that always occurs at high frequencies. So, at sufficiently high frequencies, determined by the characteristics of the coaxial cable, signals propagate without loss at a given speed, which is a pretty, it's a fraction of the speed of light in free space. All right. Now let's worry about that ratio that I mentioned, the impedance. So this ratio, which we just saw, is called the characteristic impedance of the cable, and it clearly is frequency dependent and also depends on the component values that well describe a piece of coaxial cable of interest. Well, what happens is frequency gets big. Well, as frequency gets big, you can drop this term, drop that term, and the ratio does not depend on frequency at all. It becomes a constant. And I think this is one of the most amazing results about coaxial cable and twisted pair, is that at high frequencies, the characteristic impedance, a piece of coax or twisted pair at high frequencies looks like a resistor. Notice there's no J's in there. It looks like a resistor. I find it really kind of cool that the value of that resistor depends on the inductance per unit length and the capacitance per unit length. That's the way it all works out for this model, is that at high frequencies, the piece of coax, if you had to use a Thevenin equivalent, and you look down that piece of coax, at high frequencies it looks like a resistor. Well, this has very important consequences in actually building wireline channels. Now there's a detail that I should have emphasized but didn't, is that the circuit model and the KCL and KVL equations we use to derive them assume the cable is very, very long. In other words, that KCL equation is applied at every point in space. That was very important. So, suppose you have a physical situation where you have some length of coax and you just cut the end off and you leave it open. Well, at this point, that current has to be 0 because it can't flow between the two conductors. That's what the cutting it means. What happens now, suppose the voltage, the source from the transmitter, sends this little blue pulse. And we know it's going to propagate, but look what happens because of the improper, you just cut it, it bounces back. And it bounces back theoretically with no attenuation. This greatly affects the transmission properties of the coax. You get the same thing back again, and guess what? If the impedance looking back that way is not right, it's going to bounce again and again and again. It's going to go on forever. Now let's consider the situation where I attach a resistor between the inner and outer conductors that has a resistance that's equal to the characteristic impedance of the coax. As I said, that is the Thevenin equivalent for an infinite piece of coax. So it looks like the cable goes on forever just because you attach this resistor. Now, that means that when you send that pulse down the cable, it disappears. It gets absorbed, if you will, by the impedance. So it is very important to terminate the cable correctly. You'll find this in all well-designed systems, is that you make sure that both the load and the termination resistor of value equal to Z0 is used. If not, you're going to get reflections and it's not going to work very well at all. It turns out for most coaxial cables, at least that I know of, characteristic impedance is in the range of 50 to 75 ohms. It's not terribly big. And you just need to look up the specifications for the coax you use. I've seen some coaxial cables where the characteristic impedance is actually labeled on the surface of the coax. So it's pretty easy to find out what's going on. So let's summarize the characteristics of wireline channels. They're especially designed to minimize interference using twisted pair or coaxial cable. No crosstalk. So you have privacy in a wired communication system. However, the bad news is they have to be, receiver and transmitter must be connected to the piece of cable. Like I said, you can have multiple receivers and multiple transmitters, but they have to be connected together. There's no flexibility in moving around. They're sort of tethered to the cable. If you design it well and pick your frequencies right, you have very little attenuation as long as you stay at high frequencies. If you don't, you can live that way. You'll discover, though, that the amplitude will decrease exponentially with distance. And it depends on that factor A, how far you can go. Early cables for the telegraph system back in the 19th century worked at low frequencies, and they discovered that they couldn't transmit very far at all. And their only solution, since this is before the electronics era, is they just applied a very big voltage to the telegraph wires in order to get the signal across. Interesting. Well, let's also now compare wireless and wireline. Wireless has the great advantage that you can connect receiver and transmitter at will almost, as long as they're within a proper distance of each other. There's no real limitations, no connections have to be made. You just have to understand each other's characteristics. The downside with wireline is that it does require this direct connection, and you're tethered, you can't move around. However, you have no noise and no interference. Wireless is definitely prone to noise and interference because of the linearity of Maxwell's equations. If you have an antenna, you receive everybody else's transmissions. We haven't talked about noise yet, but noise also comes in the antenna, and you get that too. Whereas in the wireline case, transmitter and receiver, basically there is no interference and there is no noise. We're going to talk about how we design now a communication system using these results.